So, welcome everybody to this second WIPAC Showcase. My name is Oliver Griefs and I'm the Executive Director of Water Industry Process and Automation Control. And I'd like to welcome Mark Hendy and Ben Smither, who are going to be talking to us today about acoustic logging, acoustic detection of leakage. So I think at that, Mark, rather than me waffle on, if you want to begin.
Yeah, no, that's good. Thank you, Robert. And thanks very much, everybody, for joining. So, Ben, if you could swap over to the next slide and just give a bit of background as to Syrinix for those that don't know of us already. So, Syrinix was initially a spin-out from the University of East Anglia. So, we've been around as a business since 2004 and became commercialised in 2009. The primary product area that we were involved in was building leak detection systems to listen for very small leaks on very large pipes under London. And a lot of sensors have been deployed over the years, and we've been monitoring a lot of the tunnelling work that was going on related to the London Underground and Thames Crossrail. So a number of systems out from that. So our background comes from large transmission trunk mains. And at the same time, we also developed the pressure transient product as well. So the system, just to define pressure transient monitoring, was really identified to sort of pick up the existence, quantify the size of transients that are causing degradation and early asset life failure. We've monitored in excess of 4,000 sites now over the years. And I think the key thing around the data is that from a very early position, we understood that the value of data and having an end-to-end solution. So next slide, Ben. So one of the things that brings the data together is this sort of constant drive of innovation. We've been bringing products through from 2 or 3 different evolutions now, and we now have our PIPEMINDER-ONE family. So the central product here is our standard pressure transient monitor, which has an internal pressure sensor. On the right-hand side, you can see the same product, but at this time it has an external pressure sensor. So if we're monitoring in deep wells or doing monitoring on rising mains, looking at pumps. And on the left-hand side is what we're mainly going to focus on today, which is our pressure PipeMinder-ONE Acoustic. So this now has an acoustic sensor, but also has all of the functionality of the pressure transient monitoring. Next slide, Ben. So just to focus in terms of the product here. So one of the key things around this being a launch of a new product was really to make it more suitable for wider deployments and easier installation. But the key thing is that we didn't want to just focus on making an acoustic product. It really brings together the value of all of the transient monitoring and all of the intelligent alerts and analysis techniques that we've built over the years, and combining that with having an integrated hydrophone for doing the acoustic correlations. The key thing around the hardware is that we wanted it to be able to be used for surveys, semi-permanent and permanent deployments. So actually it's quite a small size fitting. We'll allow it to be installed typically in hydrants and washouts in the UK, or even in the size of sort of double boundary boxes for meters. Next slide, please. In terms of the physical connection, on the underside of the sensor on the right, you can see a threaded screw thread there. So that's a 1.5-inch threaded connection. And that allows us to get into existing chambers. So we can connect into things like Sahara access points or any other infrastructure that is already available. We also have a range of adapters, so we can change the fitting to suit the local country or the different requirements on the pipeline network. The unit itself, the controller on the left, gives us our data flow up to our cloud platform radar. So we're sending the data over the cellular network using 4G, rolling back to 3G and 2G with an integrated SIM card. So we have an antenna on the device that deals with the cellular connection, but we also have a GPS antenna so that we can set the position and the clocks, more importantly, for when we're doing acoustic correlations. The key development here, though, is that we can actually also use the mobile phone network to keep our times fairly accurate so that we can, even in places where we can't get a satellite, we can still manage to do acoustic correlations on them. And then in terms of batteries and life, in terms of whether it's for short-term, long-term deployment, we have a range of batteries, both single-use that get thrown away at the end, or we also have rechargeable batteries, so that we're looking more about the whole life cost of the product that can then be charged and will typically last for many, many years. Next slide. So I mentioned Radar, and Radar is our secure cloud platform. The advantage of Radar is that you don't have to install any software onto IT infrastructure. It's all available online via user and name and password. The key thing is it can be accessed from anywhere so long as you've got an internet connection. And Radar really allows you to do all of the smart things. So we remotely set the devices up. We can update firmware, change settings on the configuration. But it also brings all the data and allows the visualization, both from graphs and maps. We integrate GIS so that we can use this for tracking events. And Radar itself also sends all of the exports out when it comes to alerts. So we'll go into the general views in a bit around the types of intelligent alert and alarms that we actually send out. Next slide. So here's an example of some of the things that we do within the platform. So on the left-hand side, sort of on the pressure transient side, in the simplest form, we catch pressure transients, which are recorded at 128 samples per second. And we have that granularity that we can drill into the data and see where in the network and which unit on a pipeline may have seen the pressure transients first to originate the position. On the top right-hand side, we're also able to use those pressure transient with the GIS to be able to then effectively run a correlation of the pressure waves of the onset of the event, which gives us a point where eventually the burst or operational flow change occurs on the network. So this is useful for picking up bursts or also identifying problem sources, be that an industrial customer or an existing valve asset. And then some of the other parts that we'll go into a bit later is the visualization from the acoustic surveys and the intelligent alerts like diurnal pressure alarms that we can pick up, as well as zone alarms. Next slide, please. So just to go through in terms of the hardware itself. So on the left-hand side, we have the acoustic sensor. You can see a hydrophone sticking out of the base of that unit. And inside is also an internal pressure transducer within that fitting. So one fitting gives us both the hydrophone acoustic data and the pressure sensor. And next to that, there is an adapter. And the adapters are then varied dependent on the typical installation. In the center, we have the controller. The controller has a sensor cable that connects the sensor. We have the two antenna cables at the top, and then a battery port to connect the battery. So the controller has a little LED on it. So in terms of deployment, it flashes the LED a range of different times and colors to let you know that the unit has been deployed. And a typical alkali single-use battery is displayed on the right, which can be connected. So all of this has been optimized to fit into fairly small enclosures like traditional hydrants. Next one. So we talked about evolution. So in terms of where this product comes from, we had the previous solution, which was another one of our PipeMinder products known as the PipeMinder T. And this historically was used more for critical trunk main monitoring for high risk, high consequence pipelines. And you can see the big black Pelly case there is actually our large Pelly case battery. So with it being for permanence, designed to give the longest battery life for that installation. The sensor head, you can see previously was quite large. And typically, if you look on the right-hand side, this is the sort of PRV or meter-sized chamber that was created to get a tapping onto the main or saddle with a gate valve to install the sensor. And you can see also a boundary box associated. And in order to get the GPS synchronized, we typically have the antenna in a boundary box so that could actually get a satellite view for each correlation. Another way of installing is to use existing infrastructure. So in the middle, you can see that this is an air valve chamber, which air valve has been lifted up and a T put into pipeline so that the sensor can be installed horizontally. Next slide, please. So now looking at the new installation. So on the left-hand side, we can still go into the same sort of existing chambers. So if you have no existing access onto the main, then typically it gives you options in terms of the size and footprint to make the physical connection. And as you can see on the image next to that with the sensor connected into the gate valve. So if you have existing connections for higher access points, that's a simple way of doing it. The middle one on the right-hand side is a single boundary box that we did with one utility to do some testing on their network. So long as we have about 600 millimeters depth, we can fit all the equipment in a single boundary box and put the lid down so it can be left out of sight. But ideally, a double boundary box would be more suitable. And on the right-hand side is a UK hydrant chamber. So this is the sort of size of the traditional fire hydrant chambers, and you can see the equipment fits in quite nicely. So what this allows you to do is in a survey mode, if you want to go out and investigate a certain part of your network using the washouts and existing hydrants, the equipment can be deployed and left there. And even if we can't get a GPS signal due to the metal lids, we can actually use the mobile phone network still to do the correlation. So that will confirm whether we have a noise source. And then there are ways, which I'll show shortly, about how we can change that installation so that we can get a GPS. Next slide. So this is the adapter for the boundary box, and you can see the coupling on the left-hand side that goes into the base of the boundary box and gives us our threaded connection. The sensor screws in on top, and then on the far right we have the antenna, which is near the surface. And these can get a good GPS signal because the metal plate in a boundary box is there for the metal detectors to find, but actually it doesn't prevent the GPS signal from being established. Next slide, please. And this is our hydrant solution. So to use hopefully the most common sources on utilities networks, there are fire hydrants or washout chambers more prevalent around than other larger infrastructure. And what you can see is we have an adapted hydrant cap, which is the blue mark on the left-hand side. So that's a hydrant cap, which then has our adapter fitted into the top of that, which allows the sensor to be installed and the rest of the equipment. And if you look on the bottom left, this is actually a company that we can work with that can go out and measure the hydrant lids, and we can refabricate or take the existing lid and machine or mill a slot into it to accept a GPS antenna. That GPS antenna then can be resined into the lid, and therefore that now will give us a GPS every day and make the correlation much more accurate because of the clock synchronization. So now we're looking at accuracies to within a meter when we're using the GPS. Next slide, please. And then from the existing chamber side, as I said earlier, we don't need such a large chamber, but for some of our utilities, this is the size that has been used in the UK for the previous versions, just to allow access. But with the thick metal covers that you can see on these, if they're in the road, you wouldn't get a GPS out of that. So typically we need to be able to bring the antenna to a roadside and use either a boundary box or some sort of above ground infrastructure would allow that to work much more effectively. Next slide, please. And just to give you a view on the different range of batteries, as you can see, the alkaline white cell on the left-hand side and the middle rechargeable are physically about the same sort of size, just one's a cylinder and one's a rectangle. And then we have a much larger rechargeable battery on the right, which will typically power this device for about 2 years in the field before it needs to be recharged. And the advantage of having the radar platform is that we can actually monitor the voltage of these batteries, so we know when they need to be visited to go and take them out and either swap them over with a charge battery or bring it back to base to charge, typically about 8 hours, and then can be installed again. Next slide, please. So that's sort of the hardware aspect. So just to go through a bit in terms of the distances and how the equipment actually works. So as you can see on the top right image, we've got a pair of sensors deployed here. This is actually on a cast iron main in a rural area, and we were picking these up about over 2 kilometers between the sensors. So what we've done for a number of utilities is to roll sensors out in a string, so we can perform a correlation, 1 against 2, 2 against 3, but we can also span 2 by having another correlation between 1 and 3. And this gives us some good confidence about what size noise we can pick up and also how far the noise has traveled. The parallelogram that you can see in the center, you can see a clear noise peak being picked up, and the small red X on that is an automated peak tracking system. So when a correlation is done, the computer picks up any peaks and puts an X on that. And then day after day, night after night, if we get consistent results being picked up, what you see on the left-hand side is a blue sort of strange vertical line with red X's through it. So this is the algorithm tracking those peaks, and we raise an alert when there's a voting system. So if we get 7 positive noise sources in the same position over 10 correlations, then the alert would be raised automatically and emailed to the client. So what we try to avoid is nonsense or nuisance alerts by just having some noise that happens at any one particular moment that might not actually be anything other than a truck idling or something going on in the network on that particular moment. Next slide, please. Now, this is the last sort of case study that I'm going to show before I hand over to Ben to go through sort of the detail in radar and everything else that we pick up. But this is a project that we conducted some pilot testing with South East Water. And you can see on the graph on the map on the left-hand side, we have 3 monitoring points. So we could see the additional distance as well as the shorter distance. This was on a 12-inch cast iron main, and the shorter pair was 1.1 kilometers. The longer pair was about 1.4 kilometers. And we conducted some leak tests on here. And what you're seeing with the parallelogram is the orange line. Actually, as we move our cursor along the parallelogram, the orange line, we can then look within the Google Maps view as to where that orange line appears. So by lining up with the acoustic noise peak, we then see in the image on the left-hand side that there is a small orange marker just at the bottom of the S of the bus stop sign. So on that correlation, we picked up the leaks within about a meter of the physical hydrant, and you can see the hydrants on the road there, on the pavement. Now, next slide, please, Ben. The interesting thing was that when we actually opened the hydrant to do this leak test, there was enough of a flow change that we saw a pressure drop, which is what you're now seeing from the use of having the triangulation algorithm using our pressure transient detection. So in the bottom left-hand side, you can see the 3 different monitoring points on the network, and you can see the pressure fall. The pressure transient that originates at the source goes out onto the pipeline, goes up the pipeline. The sensors will then detect that pressure transient, and they will send that data into radar. What radar then does is it looks at data received within that time frame, looks at the onsets of the pressure change and tags those as well as the lowest point. And it automatically runs through the analysis. And in this instance, you can see that we have a flag position, and the flag is our sort of latitude and longitude with a radius of confidence on the main. And when you actually look on the Google Maps reference for the flag, you can see that this lined up perfectly with the hydrant. So it's a really good example of the combination of the system using the acoustic noise and the pressure together. Key thing that we're looking at is, if you imagine the leaks start with small leaks where you might be able to acoustically pick it up, and if you're monitoring over a long point of time, we get a acoustic correlation and data that points to a particular place on your GIS that you can point for indication. But if that point then fails or ruptures and we start to see a lot more flow coming out, so in this instance, a burst, what we're able to do is use the triangulation algorithm to give you that burst detection. So within a few minutes of that event, an alarm could be sent out to the client. So at this stage, hopefully I've given you the view as to how the product is installed physically, the size and flexibility of the system, and a good couple of examples of the data that we've got. We've been working with a number of utilities, and we're still doing that to deploy these across the country and some of them overseas. But I'm going to pass over to Ben to take you through the radar elements that support all of this, because the key thing, as I said earlier, it's not just about the sensors out in the field, it's about the system as a whole, supported by the an analyst like Ben and his team. Over to you, Ben.
Oh, thank you very much, Mark. There's a bit of duplication here with my slides, so I'll ditch the bits that have already been very well covered by Mark. Just as said, the perspective here is more about the analysis and how we integrate with utilities at cloud level. So for quite a long time now, I suppose 10, 15 years, we've been developing products to capture specific data from water networks. So pressure and pressure transients and acoustic data from geophones and hydrophones. For a long time, it was all about just delivering the data, and the utility will deal with the analytics. But as the number of devices increase, that becomes less viable, and you need to offer more in terms of either highlighting the data that is important. So something's in this data, you need to look at it. We're not quite sure what, but you need to look in more detail, or going a step further and producing some actionable information that the utility can make a decision based on, like there's a burst and it's over here, or this pump has stopped, or you've got abnormal pressures in this DMA compared to the previous cycling and the normal expected diurnal cycling. So I'll go through, sort of just reiterate on the data that we collect, and then go through some of those sort of insights that we're able to generate from radar. So looking at the data sources, really, as Mark said, it started with acoustic monitoring for us, and we've gone through pressure transient monitoring, and now we've got a very good combined product which does acoustic and pressure transient monitoring in PipeMinder-ONE Acoustic. So that's that one. We've then got just the pressure monitoring aspect of it with the straight PipeMinder-ONE. So these run 128 samples a second, 24/7, looking at the pressure. And we report the minimum, mean and max pressure for every minute of the day. And we also have an algorithm on there looking for pressure transients and water hammer. If we see a water hammer event, we section up the data and send it straight away for analysis up to our cloud platform radar. So this pressure transient functionality is in the acoustic product and in this sort of pressure only product as well. We've then got the remote transducer version of the pressure monitoring, which does exactly the same with the data. There's min, mean, max stream every minute, and the pressure transients pulled out from our S3 algorithm. With all of the devices, we're able to take in a monitor level external data feeds. So down in the bottom left, we've got it connected to some ATI water quality probes, so turbidity, chlorine, that sort of thing. We can also take in flow data from pulse output flow meters. So if we're monitoring a pump station, or even DMA entry or in networks, we can pick up flow data and send it back with the pressure data to radar. And then at a cloud level, so this is directly into radar, we can bring in other time series data and event-based data. The really cool stuff is the SCADA data. We can overlay SCADA events with pressure transients to give you more of an insight as to what might be causing the pressure transient if it's your own activities. Okay, so that's with the sort of data sources. The next few slides will look at some of the analytics that we can do. This first one, zone alarms, is actually applied at a device level, but it's tied in all the way through radar and then out via email alerts and the API alerts to customers. And the basic concept with a zone alarm is that you've got 4 configurable thresholds, which define these sort of 5 zones. And when the signal, for example, pressure, enters each of those zones, you can decide what to do. So you could say define zone 3 as your normal operation zone, and we'll do nothing. We're expecting the pressure to be within those upper and lower bounds. You could then define some higher and lower zones where perhaps when you enter that zone, we'll send an alarm, or you can send continuous data. So it means when you start to deviate from your normal expected pressures, you could start to send continuous summary data about every minute so that you can track a potential fault. And when you get to the very high zone, you could send an email alert as well to say that someone really needs to be looking at this now. And when they go there, there's some data leading up to it. So you could configure these for, too low and too high alarm levels, or you could set them up to have 4 high alarm levels if you were looking at, say, turbidity, and you were just interested when the signal is high and not when it's down near zero. So those are zone alarms, and they result in email alerts basically coming out of radar. Once we get up to a radar level, we've recently implemented steady state alarms, or diurnal cycling alarms, and these are looking at the natural cycling of pressure within a DMA normally over the course of a week or two. So with a DMA and somewhere where you've got a large number of customers and you've got this sort of averaging of the demand, you do see a very repetitive cycling of the pressures day on day. And for each 15 minutes of the day, we look at the same time slot on the previous 7 days, look at the range of pressures that have been seen for that time slot and predict what we should be seeing for the current day. And it's basically a zero configuration change monitoring tool. So once you've got 7 days of data, it's got enough sort of history to learn roughly what the network should be doing at that location. And we set some upper and lower limits for each 15 minutes of the day and alarm if the current pressure deviates from those historic limits. And then it's a sort of rolling system. So obviously, if a fault happens or you decide to change the operating pressure of the DMA, you'll get a step change. But after 7 days, it will have relearned the new normal. And those are tied in again to alarms via email out of radar and the API. When it comes to pressure transient events, we've got an example here in the top left. So you might find you have a pump stop, a sudden drop in pressure, which travels as a wave around the network. So when you get a sharp change in pressure, I'm talking about something, half a bar or bigger, either up or down change in pressure, and happening in less than a second normally, something like 0.2, 0.3 of a second. It can be longer. And that will travel as a wave around the network. So this water hammer event will travel at 1,000 meters a second in cast iron, and it will then hit junctions. When it reaches a junction, some of that energy of the wave will go down each leg, but the amplitude will be reduced. So by looking at the way that these waves propagate through the network, we can work out where they've come from, as Marcus said. So we have the GIS data in radar. When a sudden change in pressure occurs, we can see the arrival of that wave at the monitors, and we can triangulate the source of it. Now, for us, this is in radar tied up into what we call a network event. And these are a sort of a time slice of a few minutes. If we have some transient data come in from several devices in the same 2-minute window, several minute window, we'll group it together into a network event. The first step is we'll look at the SCADA data that we might or might not have, telling us what network activity there is. So in this case, you can see we've tagged a pump event. We'll then triangulate it, see if we can get a location. So we'll look for the onsets and triangulate the location. And then the last thing we do is look at the shape of the transient and compare it against a library of shapes. It's not a very good example, this one with the shapes, but we have good sets of sort of pump stops, which is a drop, maybe a ring, pump starts. So we can give you an indication of what we think just based on the shape the event is. The idea of a network event is it pulls all of this together in one place, so that you can, on one page, have the best go at working out what's going on and what's caused the sudden pressure change. And again, we've got email alerts tied into this, and goes out via the API on radar. With pressure transients still, so we're still looking at water hammer here and not the acoustics. We often get asked about deployment planning. Where do we put the devices? How many do we need? What kind of coverage do I get? So there's some pretty simple models that deal with wave attenuation, as I was describing. The wave as it hits junctions, the energy splits in two directions and the pressure wave gets smaller. And a really key point to take from those models is that when a wave is on a small pipe, so you've got a 3-inch main with a 1 bar pressure drop flying along it, if that joins a bigger pipe, say an 8-inch pipe with a big increase in cross-sectional area, that event can almost disappear. It's a very small pressure change then once it hits the 8-inch main. So these deployment planning tools correct for all of that, or calculate all of those effects. And on the left, we've got an example where we've placed the monitors on the bigger mains in an area. This is an American network. And you can see that it gives you very little visibility into the distribution mains that connect onto the transmission mains because of that amplitude decay as the waves travel up to the monitors and onto the bigger mains. On the right, the objective of the same 15 monitors was to monitor the distribution systems. So if you want to do that, you have to put the devices on the smaller pipes and you have to put them closer together. And then you can have good visibility of distribution systems. So tying this all together, as Mark was showing earlier, we've run projects with a number of utilities where, first of all, we've planned deployments for pressure transient monitors. So on the left here, we're looking at a DMA at Aviles. And then we've gone in, once the real deployments have happened, we've gone in and simulated burst events by having fast valve operations. So fast opening of valves, you create a sudden pressure drop, which travels through the network and then triggers the triangulation in radar. So it's sort of a proof all the way through for customers. Now, the thing to bear in mind with these is there's a sort of order of magnitude thing, a scaling thing between pressure transient triangulation and the acoustic correlation, where we're looking at the leak noise and producing the correllogram and showing the peaks. So with triangulation, you're looking at larger, they've got to be flow changes. So it's got to be a step change in flow, creating a pressure wave. And we're normally looking at stuff 0.5 litre a second and up, probably 1 litre a second and up for the flow change, for it to become detectable in the network. Whereas for the acoustic monitoring, where we're listening to the leak noise, first of all, the leaks can be pre-existing and pre-running. So we can just listen to the noise and correlate it. And the second thing is there could be much smaller flows. It could be down in the sort of 0.1 litre a second sort of range, and it's still very detectable acoustically. And so that's where we sort of got to with these projects that Mark was outlining. So I think you've already seen this slide pretty much showing the correlation now of a very small leak running on a asbestos cement pipe. So 2.2 kilometres apart for this one. Got another example on PVC. The interesting thing with PVC is it's more absorbent as a material for the acoustics. So the acoustic energy doesn't go so far, so you have to put your sensors a little closer together. And we're starting to build quite good models for this too. So not only deployment planning for the pressure transit side of it, but we've got a good understanding of acoustic systems and how far apart to put these monitors. In terms of the acoustic analysis, I thought it'd be useful to show you a few more bits from radar and how we manage points of interest and peaks in radar. So as Mark's shown you, on the left in the background here, you can see a peak that's being tracked. It's actually the lower of the two peaks with the cross on it. The left-hand end here, where you've got this, which is near the first site in the monitoring pair, is actually an end peak. So this is noise that's come in out of bracket, and it tends to bunch up at one end. And that's a feature you get with all correlations. You'll see if there's lots of noise on the network traveling through your monitored section, you'll see what are called end peaks at each end. So in this case, the point we're interested in is actually the secondary peak that's maybe 70 meters away from the end, but a little smaller. And what you can see is in the middle here, we've sort of zoomed in, and you can see the what we call the B scan, where the date is on the y-axis, and on the x-axis is the position along the main. And you can see one correlation overplotted for a specific day, in this case, the 29th. Then all of the other correlations for the other days are shown in this sort of coloured plot, like a waterfall plot. and you can see all the points of interest tracking through. So it tends to run a sort of string of points through as we track points of interest. And then again on the right, actually we're plotting several parallelograms here from several different days. And on radar, all of this, as you saw with Mark, is these points of interest. You can click on these plots and tie it into a geographic location on the map. So once you've got a point of interest and this 7 out of 10 day test has passed for the leak, we've got a persistent peak in the same position. So we're now in leakage rather than pressure transient. We've got a set of tools for managing it on our leakage dashboard. So first step is a suspected leak has been identified. And then we have this sort of triage system where we can say what the status of that leak is. Has it been confirmed? Do we know what the source is? And how important is it? Is it a critical one or not? And on each of these events on the dashboard, you can click on them and we get a separate page up to manage it and manage the resolution of that leak. So it might be that you've identified a known noise source on the network, and you've got a PRV, or perhaps you've got a takeoff with some flow noise from the takeoff, or you've got a real leak which you need to go out and fix. And so just a bit more detail here of these leak events. So the most important thing with these leak events is it gives you a sort of history of what's happened on the pipeline. So if you've got a point of interest that's been generated by a takeoff or an unstable PRV, and you've gone in and resolved it, or a partially open valve is another good example, you might find that leak reoccurs months later. And in that case, we've got the ability to sort of we have the record of these points of interest, and you can see the historic ones laid out. So you can draw much faster conclusions about what might be going on, or start your investigation with a bit of a heads up as to what's previously happened on that pipeline. Okay. So really the last thing I wanted to show was this sort of integration slide that describes the whole sort of flow through and our typical interaction with water utilities. On the left-hand side here, we've got the data sources, which is for us now PIPEMINDER-ONE. We've got the acoustic data, we've got pressure data, we've got external flow data that's come in via the pulse inputs, and we've got potentially water quality data as well. So that all goes in over 3G, 2G, 4G to radar. We also push all the updates, software updates to the PM1s over the air, and the configuration changes over the air. Then within radar, we've got all of our machine learning and AI algorithms running, generating the different event alerts that we've got. So we've had a really good look at the leak alerts, and we've got the zone alarms which run on the device and give you the 5 levels of zoning, steady state alarms on the device, on radar, looking at the typical cycling in a DMA, and on networks. We've got network events, which is where all the triangulation happens, and the SCADA overlay and classification of the shapes. And then we've got something we haven't spoken about is burst and performance alerts for rising mains. So we've got algorithms looking for the typical effect of a burst on a rising main delivery pressure. So then within radar, we also have quite a few ways that we tie into customers. We've got obviously email alerts going out for the different things we detect. And we can do all of that automatically as well via APIs. So APIs that you can connect to with your systems, and you can pull alerts out, and you can pull data out of our cloud platform, your data out of our cloud platform into other systems. And as we've seen, we can also push data back in again, or pull data back into radar. And you can push SCADA data in, and you can push time series data into radar for plotting against the data that's been collected from our devices. And really, the next steps for us are about that integration and about designing better and improved algorithms. We've for the last 4 or 5 years, we've had a very open approach to the data going out to customers, and customers having complete freedom to use the data how they need to get the value from it, and hence the API. And we've been working very closely with customers to learn about the algorithms and improve them and create better training sets to improve the algorithms. Yeah, I think that's pretty much it. Is there anything else you'd like to add at all, Mark? I think we're...
No, I think you've covered it, Ben. I think let's just see where the questions are in reality.
So thank you very much, Mark. Thank you very much, Ben. Does anyone have any questions? Do unmute your video, unmute yourself, and yeah.
I have a question. Perhaps you said that I didn't understand. I imagine the higher is the pressure in for example, in the bulk, the clearer will be the acoustic sign of a burst, of a leak. Which is the minimum pressure that is needed for the system to operate?
For the leak detection, for the acoustic leak detection?
Yes.
Yeah. Okay. I think it's sort of in the order of sort of 1 or 2 bar. We can't do, obviously if the leaks are running it and there's only just above atmospheric pressure, only just above atmospheric pressure in the pipe, then we don't get very much leak noise from the leaks. So you need some positive pressure in the pipeline to be able to generate a leak noise. But yes, sort of 1 or 2, maybe 2 bar absolutes and upwards.
Okay, thank you.
But the increase in the pressure does make the leak noises louder and more detectable.
Right.
Okay, is there any more questions from anyone in the audience? No? So then, Mark, obviously leakage is a massive area of investment in the water industry, probably from now and forever, and actually has been. Where do you think we are on leakage nationally? How do we get better?
Good question, Oliver. I think the main challenge, I think, is to change the way that we currently operate. So I think going out and fixing leaks all of the time that reoccur because the causation is not addressed. And I think that's particularly something that we bring to within our solution by being able to identify sources of transient which essentially cause the leaks to originate in the first place and cause degradation in the pipeline is a big start. So we are starting to see change in the way that networks are being looked at in terms of network calming exercises as well as leakage detection. And I think what we see more and more as the years go on is more where it works hand in hand.
So it's more understanding the root cause analysis of why something's leaking, and then using that data. I must admit, I know we've got somebody from a PAL on the meeting. I love the work that Andrew Donnelly did over in Lisbon. And that sort of work was stunning as they got down. Okay, you can argue water companies in the UK don't just operate on a city scale. They work over very large areas. In Lisbon, I think they went from 24% down to about 7% leakage. And I always think that is a stunning case study. We've got a question from, I think, Yorkshire Water. Can you give a rough indication of battery life? Even a range for each type of battery is helpful. And the question, what's the approximate cost?
Okay, yeah. So in terms of the batteries, the alkali cell is designed really to last about 8 months, where you would be doing a couple of correlations a night and sending data 4 times a day and reducing the number of transients. So obviously the battery performance will vary based on how much time it communicates, how many correlations you do, the signal strength, etc. So it's a bit fairly flexible. The small rechargeable batteries, similarly, we're talking in the range of sort of 8 to 9 months before you would need to recharge it. The large Pelicase one would last in excess of 2 years. In terms of typical costs, I mean, the alkali batteries typically cost something in the range of about 130, 140 pounds. The rechargeables are about 400, but the large rechargeables, they are quite pricey. I can't quite remember what they are, but obviously they're designed that you buy it once and it will last many, many years to come. So it's really designed for the permanent monitoring where you're looking at asset criticality and no operation or return visits. But I can certainly let Katrina know in terms of pricing.
Good afternoon. I have been lurking in the background, listening intently, as is my wont, not saying much, which is not like me. Can I just ask you a quick question, Mark, and maybe anybody else on the call? Where do you think we are with regards, I actually don't use the word battery very often. I just call it the B word because it is it should be actually be a P word, I suppose. It's a bit of a pain. Where are Syrinix and the industry in general with regards to energy harvesting as opposed to slinging tons and tons of lithium into our water distribution network? Where are we with that, Mark? You must be, in that world.
Yeah, well, I'll answer first and then hand over to Ben for a bit more detail, because I think as an industry, we keep being asked the question. Some utilities are very interested in going down renewables. We certainly have explored using pressure variation at PRVs, using things like microturbines to trickle charge batteries. We are also using solar power. So we're about to do projects currently out in the Middle East where we're hooking up the acoustic systems to solar panels. So effectively it means that the battery won't need to be recharged. And we have done so in America. So I think those are the avenues. I think that there's a bigger case to say is can the industry design chambers for the future with renewables built in? And that's something that one utility engaged a couple of years ago, but I don't think it really ever went anywhere. Because I think there's got to be drive by the whole industry together to get that sort of innovation forward, I think.
Yeah, I mean, and obviously with my background, I know quite a lot about that, but it still involves a battery. So we're still fundamentally powering from a battery, and then the renewable is doing its stuff to trickle charge. So we're still opening lithium mines in Cornwall because we need lithium. Maybe more for Ben. How close are we to getting devices which maybe use, super caps, devices which do away with the battery completely? So a renewable might be directly powering the device. How close are we to that, do you think, Ben?
What sort of time gap do you need between the availability of the power source? I mean, we have looked at all sorts of things as energy sources. Obviously, you can get away with if you've got something that gives you a fairly reliable cycle of energy every day, like solar or wind, maybe once, with a week sort of gap. The batteries could be much, much smaller, so you're using far less of the precious metals. The other thing, we've tried several things. We've looked at, obviously on PRVs, you get a pressure drop, so you can put an impeller in and get some energy from a micro turbine, but that's only really available wherever that pressure drop is. You don't get that in the network unless you've got a throttled valve or something. So we might have it in 1 or 2% of the installation points, but not everywhere else. On pumps, there are vibration energy harvesting systems, which we've looked at, but you're not always next to a pump. And so they all have their sort of pros and cons. I think solar is probably, it suffers from theft in some places, but in other places it seems to work very well. Seems to be the obvious one to use.
I was watching, I can't remember if it's a current program. It was Top Gear. I don't normally watch it, but I've got past my boys' toy stage. But is it the latest Lamborghini or Ferrari is actually running off supercaps? There's some supercar is currently running off capacitors rather than batteries.
Well, they have a very high power density, don't they? The density is a bit lower than sort of normal battery technologies.
Because at some point, this. Yeah, go on, Oliver. Sorry.
I do remember this was being looked at a few years ago. That Jeff Haswell of PipeMinder, he's no longer operating anymore, but he was looking at piezoelectrics from the vibration in the main. but it never really took off, unfortunately. And he was looking at a sort of sensor level. Laurie, you got your hand up.
Yeah, no, I was actually going to raise the story of Peter Tag myself.
Yeah.
The only reason it didn't go forward, I mean, it was all ready to go. It was the prototype was working well, but that was using like a tuning fork into the flow, which was then causing an energy source which was harvested in the piezo tag device external to the pipe. And I was going to ask exactly the same question, that surely where we're dealing with flows in pipes and quite a lot of energy in the pipe itself, that actually all those transients could be harvested as an energy source for ultra low power devices. I'm surprised it hasn't actually progressed further than it has, to be honest.
I don't know what happened with Piezo Tag because
he actually did. I spoke to him a few weeks ago, and he's actually doing very well in pressure tire monitoring of heavy trucks.
Yeah, so, he always, that was his main area, and I think
that business took off, and the water industry was developing very slowly, and so he decided to park it and follow the money. Quite wisely. Very sensible thing to do.
Absolutely, yeah.
Anyway.
Any more questions, anybody?
When can we all go to a pub again?
When can we all go to a pub again? As soon as you like, apparently. Might, but I'm not guaranteeing you won't get COVID. So at that, if there's any more questions, then I've put Ben and Mark's contact details on LinkedIn in the chat window, so do use that. This video has been recorded and it will be up on YouTube as soon as I can get it up there. If there are any other companies who want to endure the WIPAC Showcase, then please get in touch with me directly through LinkedIn. It's painless, isn't it, Mark? Isn't it, Ben?
Yeah, all good. Thank you.
It is painless. Yeah. So, do keep an eye out for the WIPAC webinars and the WIPAC monthly, obviously, it comes out every month. So thank you very much, Mark. Thank you very much, Ben. I hope everyone's enjoyed this, and watch out for the recording on YouTube.
Yeah, thank you, Oliver. Thank you, Mark and Ben.
Thank you, Oliver.
Thank you very much.
Thanks very much, everyone.
Thank you. Thank you.
We'll see you in a pilot project.
Definitely. That's a sale, Mark.
Thank you.